Welcome everyone to this first video of this 10-part series on convective wildfires. My name is Tristan Rulos, and today we will start to explore the fundamental question of why do plumes rise. Understanding this will give us an edge when we want to predict the risk at convective wildfires. To understand why plumes rise, such as during the Ponte Vilomara fire for example in 2022, we have to get back to the ancient Greek scientist Archimedes, who came up with the concept of buoyancy. So in this video, we will start to explore the concept of buoyancy as defined by Archimedes. We will see how we can translate this to explain convective wildfire plumes. And then in the end, we will also try to replicate this at home and see what we can learn from that. So, what is buoyancy? To understand that, let's have a look at a box of standing air with an air parcel inside of it, where the density of the air parcel is equal to the density of the environment. If we now add a wildfire below the air parcel, it means that we would warm up the air parcel. And to understand what this means for the air parcel, we have to realize that the density of an air parcel is inversely proportional to the temperature, meaning that if the temperature rises, the density drops. So in this case, when we add the wildfire, this means that the density of the parcel becomes smaller than the density of the environment. In other words, our air parcel is lighter than the environment, which means that it's positively buoyant. It will start to rise upwards. And that is what we refer to with buoyancy. It's a force that develops when there is a density difference. To translate this to reality, I will make use mostly of the temperature, not of the density, because temperature is the more intuitive unit. If an air parcel is warmer than its environment, and thus less dense, it is positively buoyant and will start to rise. So let's have a look at the plume that I showed before from the Ponte Vilomara fire in 2022. If we start at the surface, we know that we have a fire that heats up the air parcels directly above it, making them warmer than the environment and thus positively buoyant, resulting in the convective motion that we observe in the field. While these parcels rise, we know that these parcels cool down, and this means that the parcels will rise until they reach the same temperature as the environment. Looking from this figure, that happens approximately at point B, where the parcels become of equal temperature as the environment, meaning that they will not rise any further, and instead the air parcels are transported horizontally away in the direction of the wind, which visually results in this horizontal smoke layer that we observe with plumes. At this point, we have discussed the fundamental concept of buoyancy as defined by Archimedes. We have discussed how we can use buoyancy to explain visual observations of convective plumes. And to me, now the most fun part of this video starts, which is to replicate buoyancy at home. What you will need for this is a bucket of water, preferably transparent, and a football or any other ball that has air inside of it.
So I have here a football and a bucket of water, because all we now have is basically an air parcel that is lighter than its environment. If we push this air parcel that is filled with air, this football that is filled with air, into the water. So basically we could say that this is representing a relatively warm air parcel that is warmer than its environment, in this case the water, because it's less dense than the water. So if we put this football below it, and we notice this directly, by the way, when you put the ball in there is an upward force, which is the buoyant force of the football. So if we let the football go, we see that it starts to jump out of the water. And what is interesting here is that we theorized in the previous slides that when we release a warm air parcel, it will rise and it will stop at the moment that it becomes as dense as its environment, which for the football would be at the border between the water and the air, right? Because this football is denser than the air above it, but less dense than the water itself. However, what we saw in the experiment is something else. We saw that the football built up momentum, And because it has a vertical velocity, instead of stopping here, it will jump out of the water, where it will be denser than the environment around it. And that means that in this case, it becomes negatively buoyant. But because it has a speed, it will just slow down till it reaches a vertical velocity of 0, being basically at the highest point that the ball reaches. And then at this point, it will start to drop back down towards the level of neutral buoyancy, which is basically the level, the water level, where the football is less dense than the water below it, but denser than the air above it. So it will stabilize here. Let's have a look how we can translate this experiment, what we just did, towards wildfire plumes that we see in reality.
I hope that the experiment went well for everyone at home. And let's now translate what we saw with the experiment to the plume that we discussed before from the Pont Vilomara fire in 2022. When we put the football inside the water, we artificially created an air parcel that was lighter than its environment, like when the fire heats up the air above it, right? And similar to that, the football started to rise because it's less dense than the environment and thus is positively buoyant. It kept on accelerating till it reached the water level, but because it had a momentum at that point, it jumped out of the water, it jumped above it. At that point, the football, then the air, meaning that it becomes negatively buoyant and starts to decelerate till it reached the point where the vertical speed was 0. But at this point, the ball was still negatively buoyant, meaning that instead of rising further, it dropped back down towards the water level. The level which is for the football the level of neutral buoyancy. Because at this point, it is denser than the air above it, so it cannot rise upwards, but it's lighter than the water below it, so it will not sink down, meaning it's at a neutral level. And this behavior of the football that we witnessed during the experiment also explains why the highest part of the plume is higher than the level, than the height at which the horizontal smoke layer develops. The plume first overshoots, becoming negatively buoyant, and then stabilizes around the level of neutral buoyancy, where we see a horizontal smoke layer developing. So, to summarize our findings today, we have seen that buoyancy is critical to explain the observed plumes, but we have also noted that the ability of a plume to rise is dependent on the difference with the environment. So in the next video, we will discuss how the environment looks like in the atmosphere. And of course, a very valid question would be, what about clouds? What happens when we have a pyrocumulus or a pyrocumulonimbus on top of my plume? Does that influence things? I would say yes, but we will discuss the details in this in part 3 and later episodes. Thank you all for watching and have a nice day.